In our second example of how to apply Newton's second law, we have an incline. We have a mass on top of the incline. There's no friction between the mass and the incline. And we want to know how fast this mass is going to be accelerating down the incline. So again, we want to indicate all the forces acting on that mass. Well, let's see here. We have the gravity acting downward. So we have mg, which is the weight of that object. Now, since it's on an incline, we really should draw the components of that vector. So typically, we could say this is the force due to gravity, and we'll write it like that. So you can see that this is a vector quantity. So we want the two components, the one component which is perpendicular to the slope, and the other one component which is parallel to the slope. So that means we're going to draw this component right here, which is perpendicular to the incline, and here this is the component which is parallel to the incline. If you go ahead and then draw the parallelogram right here, you can see how these are the components. Now, how do we find these components? Well, because of similarity here, you can see that this triangle right here is similar to this triangle, which means that this angle here is the same as this angle here. Another way of looking at that is noticing that this line right here is perpendicular to this line, and this line right here is perpendicular to this line. So if those two are perpendicular to these two, that means the angle included must be the same, so this is theta. Notice this is a right angle. That means that this is the adjacent side to the angle. This is the hypotenuse, which means that this here is mg times the cosine of theta, which makes this mg times the sine of theta. All right. Now also, we have a reactionary force. So the force pushing down an incline from this mass is this vertical or perpendicular component, which means we have a normal pushing back in this direction. This is the normal from the surface pushing back, and that will also be in magnitude equal to mg cosine of theta. Notice that it's in the opposite direction, which means that this component, this cancels out this component right here, which means that this is the only net force remaining on that object. If that's the only force remaining on the object, that's the force causing the acceleration. So now we'll go to our Newton's second law equation, F equals ma. In this case, F is going to be mg sine theta. So we have mg sine theta equals ma. And of course, we're solving for a. That's the objective right here. So then you see that the m cancels on both sides, and we're left with a equals g sine theta. All right. Now, if we plug in what we know, theta is 30 degrees, so this is equal to 9.8 meters per second squared. Multiply it times the sine of 30 degrees, which is 1/2, so this ends up being 4.9 meters per second squared. Now, another interesting thing to look at is to look at limiting cases. In physics, it's always a good idea to look at limiting cases. What would the acceleration be when the angle goes to 0? Of course, when the angle goes to 0, then there would not be any incline. We expect the mg sine theta to go to 0 as well. And sure enough, the sine of 0 degrees is 0, so there would be no acceleration. What would happen if this angle became 90 degrees? Well, if it became 90 degrees, then it would be like free fall. Now, the sine of 90 degrees is 1, and therefore, this would go to 1, and acceleration would equal 9.8 meters per second squared, which is, of course, acceleration due to free fall. So you can see that when you look at limiting cases, it helps you understand the situation as well. So here, again, a nice example of how to utilize Newton's second law.